Welcome to Lecture 5, Part 1 of the Neurodynamics lecture series. In the last lecture we simplified the Hodgkin-Huxley first by using the adiabatic assumption and making it one-dimensional, and then we decided to include a second variable, a slow variable, to model the downstroke. The reasoning behind that was that we have two slow variables that behave approximately the same in terms of the timescales, and we choose only one of the two. Both have the effect that we produce a downstroke and after hyperpolarization. This gave us finally an equation where we have the first part that was coming from the adiabatic assumption, where we expressed p by p infinity, assuming that p is changing so fast that its own dynamics can be neglected. And we added the second component, which was then dependent on n of t. To remind you, this then required that we assumed that, first of all, only one of the two, m and h of t, had been used, and that only one of the two slow variables, which are h and n, is used, which was so far a model description, a model assumption, which we did because we just said we're modeling the most simple solution possible. In the next slides I will motivate better why we used exactly these two and what alternative we would have had. Before we do this, I would like to rehearse again how we actually use then this two-dimensional model to simplify it further, coming to a Fitch-Naguma model. The basic idea was that we computed the null clients, which is all the set of points for which, for example, the voltage or the n is not changing. And we computed an expression as a function that computes an explicit dependence between n and the voltage that we have in these places. And this not only for n, but also for the V null line. These two null clients that we computed analytically gave us these two shapes, which had been tailoring the entire phase space into four different parts. And in each of these four parts, we had uniform behavior in a sense that for region A, both the voltage and the n is increasing, which corresponds to the upstroke. In region B, the voltage is decreasing, but n is still increasing, which is the initial phase of the downstroke. And region C is the after hyperpolarization, where the voltage is still decreasing, but n starts to decrease as well. And then last but not least, region D, which is corresponding to the phase where the neuron is sensitive for new input. So having this in mind, we then decided that instead of modeling and simplifying the neuron in an analytical fashion, we identified that we need these four principal regions, and we were looking for a more simple way to actually construct null clients that look similar and tailor the entire phase space into similar spaces. And the first approach was the Fitch-Naguma model that replaced the curved line that you see here for the n null client with just a straight line that you see here. And this straight line, of course, is only very different only at this region here, where the line is kind of strongly disagreeing with the curve here. Nevertheless, the four different regions A, B, and C are exactly the same, and the principal behavior in these regions is also the same. So having said that, that means we can actually come up with a very simple linear relation between the W dot and the voltage, and we can come up with a more simple expression of the V null line as well, because the INAP plus potassium model is using an exponential in the denominator to produce this very nice curve. And giving its principal shape, we realize that we can also do this with a polynomial, which allows us to actually understand the factors more easily. Okay, coming back to the choices that we did in terms of the inclusion of the slow variables. Here again we see the Fitzhugh, the Hodgkin-Huxley model, and you see that the Hodgkin-Huxley model has 4 different differential equations. The voltage plus the 3 gating variables. If we do the analysis in terms of the timescales, we realize that the voltage is rather slow, and the timescales of the gating variables of n and h are also rather slow and nearly identical, while the timescale of tau m is much faster. So this alone allowed us to actually use combination of these and to try to simplify the choices that we were really considering. This diagram shows you the potential choices that we could have done. On the left hand side you see the first one, that is remove n. If we remove n, then actually we're left, and then actually this is gone. Since this is h to the power of 1, this is gone as well, which means we are left with an equation that is composed of the sodium dependence, where we have a product of 2 gating variables, plus the part where we have a leak current and the input into the neuron. In principle, this is okay, because m of t is fast and h of t is slow. And that means we could in principle model an upstroke that is due to the self-amplification and a downstroke that is due to a strong inrush that is compensating the self-amplification of the membrane potential. And because it's much slower, it cannot damp the self-amplification immediately, but it needs some time. So it's exactly the requirement of a fast and a slow time scale using m and h would be fulfilled. However, looking at the remaining differential equation, we see immediately that we would have to consider the product between the result of the 2 gating variables. That means we would get a rather complicated differential equation which we would have to solve. Therefore, removing n didn't look too attractive to us. And actually that's the only reason that it didn't look attractive to us. The alternative is that we are removing h. If we remove h, then we have the situation that we have this part here removed. This part was 1 anyway, because it was h t to the power of 1. That means we have a fast gating variable here, a slow gating variable here. That is the minimal requirement for modeling a down and an upstroke. And we have 2 parts that are now additive. The first part that is just dependent on h, and the second part that is just dependent on n. Much more convenient in terms of solving a differential equation. Has the same purpose, a slow and a fast variable. And since it's easier to solve, we just decide on removing h instead of removing n, which is the INAP plus K model that we studied. Well, what we forgot is that, of course, the activation gating variables can have different functions in respect to the possible inward and outward currents, which are essentially determined by the concentrations of the ions in the inside and the outside medium. So that means we can, of course, on the one hand side, argue that we want to have a simpler model like we did on the previous slide. On the other side, we still have to actually discuss the consequences of the possible inclusion of this multiplicative dependence, because the activation due to a different gating variable may have different consequences. To see whether that is indeed necessary, we will now try to understand the consequence of an activation and inactivation for M and H as the two gating variables in the four possible conditions that actually we are dealing with an inward and an outward current. Before we get into detailed analysis of that, I need to introduce a concept which is called a negative conductance. A negative conductance is a conductance where we have a negative slope in the IV relation. That means the voltage is increasing and the current is decreasing, which is a kind of counterintuitive situation. In high school, we learned that with increasing voltage, given a certain resistance, the current through the system is of course increasing as well, which is corresponding to a positive conductance and a positive IV relation. Let's remember what we learned in school. In school we learned that if we increase the voltage, that the current is proportional. That means we have a linear relationship between I and V corresponding to a constant current. This has a positive slope and therefore is a positive conductance. Of course, this is not always the case. If we have, for example, some nonlinearities, or if the device, for example, depends on temperature, then the current cannot grow beyond any limit. And therefore, you also all very often have such a sigmoid-like behavior that if the voltage is increasing across a certain bound, the increase in the voltage is limited. The increase in the current is limited. That means we have a bounded growth in the current as a function of the voltage. Nevertheless, this is still a positive current. It would be negative if the behavior would be like that. That means from a certain point on, the current would be decreased even if we increase the voltage even further. Then this phase, where we have a negative slope from here, we would actually call this a negative conductance. A rather counterintuitive scenario for normal resistance. If you talk about a wire or if we talk about a resistor in electronics. However, since we talk about a dynamical system that is implemented with some kind of like biological machinery, of course it can happen that there is a certain feedback loop that actually will induce such a negative conductance. And exactly this feedback loop we will study now. For that we actually look again at this very same table where we have input and outward currents and where we have gating variables. And we first characterize the functions in terms of what an activation for an inward current will lead to. Well, an activation of M for an inward current will lead to a depolarization. An activation of M for an outward current leads to a depolarization. So to study now if that is a self-amplifying loop and therefore associated with a negative conductance, or whether that is a loop that is self-terminating and therefore associated with a positive conductance, requires us to study the sequence of actions and consequences that a depolarization will induce. We start with a depolarization for an inward current. A depolarization for the inward current will increase the activation of M. How do we know this? Well, this knowledge we need to deduce from the differential equations. There you see what a consequence of an increase in the depolarization of the voltage has on the differential equation of M. Since this is hard and involves an analytical understanding, I condense this here and actually highlighting the sequence of events that is happening. So a depolarization causes an increase in M, which you see in the plus. An increase in the activation M has a consequence that you have a stronger inward current. And a stronger inward current produces a stronger depolarization. And we close the loop. That means a stronger depolarization again increases M, and an increase in M and stronger inward current, which means an even stronger depolarization. So that means we have a positive feedback loop. Depolarization causes even stronger depolarization to happen based on the activation of M. So the alternative combination would be to study an inactivation of H based on the outward current. So the difference is different gating variable in different direction of the ion flow. Therefore, we are studying a hyperpolarization. So if we have initial hyperpolarization, this will increase H. And if we have H increased, this will increase the outward current, and an increased outward current will further increase the hyperpolarization. So again, you see it's a positive feedback loop. Hyperpolarization causes stronger hyperpolarization. Quite the opposite happens for the two remaining cases. Let's start to study the activation M and an outward current. We start with the depolarization, which again, of course, causes an increase in M. There is no difference because so far we are just concerned with the gating variable. An increase in M is causing a stronger outward current. Still, just concerned with the gating variable. But the effect of the increased current is different. Since it's an outward current, we are causing the system to have a less strong depolarization. That means we have a negative feedback loop. That means depolarization with an outward current is leading to less depolarization. The very same for the inactivation. The right hand side here and the left hand side here is identical up to the last and final effect of the current. So that means the hyperpolarization again produces an increase in H. An increase in H makes a stronger inward current, but the effect of the inward current is a reduced hyperpolarization instead of a stronger hyperpolarization that we saw on the right hand side. So that means this is also a negative feedback loop. So as a consequence of that, we have two combinations that lead to a positive amplifying loop, a self-amplification, and two that are leading to a resonant loop. That means it's reacting with the negative sign to a drive. Both will have rather different principles in terms of computation properties, while the amplifying cases will lead to neurons that like to have very many spikes in a very short time and then react strongly to it. The two reddish cases that behave in a resonant fashion like to get activity with a certain temporal profile. So that means we now understand that we can, in principle, based on the timescales of the system, either ignore H or ignore M. However, if we consider this in more detail, we can, with both cases, model amplifying and resonant cases. So that means, dependent on the direction of the current that we choose, even if we restrict our system to either M or H, we can model both dependent on whether we are in the inward or outward current situation. So that means, from the last slide, we can still argue that we want either M or M, and based on the exact parameters of the system, we can make the system either amplifying and resonating for both cases.